The mole is used to count incredibly large numbers of things like molecules and atoms. It's the exact same idea as a dozen, where a dozen is 12 things. Well, a mole is exactly 6.022140076 times 10 to the 23 things. That number seems rather arbitrary, and it sort of is rather arbitrary. It's based on, originally, the definition was the number of atoms in 12 grams of the isotope carbon 12, which is a carbon atom with 6 protons and 6 neutrons. The number on the top there is called mass number. It's not the same thing as mass. It's called mass number. And you get it by adding up protons and neutrons. The number on the bottom right there is atomic number. That's just the number of protons. This is not actually the definition of how many things are in a mole anymore. In 2019, the SI system redefined 1 mole to be exactly this number with no uncertainty. There was a big redefinition in 2019 where they defined a few constants to be exact numerical values. And the long story short, that allowed them to get rid of the kilogram being defined as a chunk of metal. It's no longer a specific chunk of metal in a vault in Paris. Now the kilogram is defined in terms of some of these constants that we defined for sure in 2019. We don't need that many digits of precision in IB physics. So if you look up Avogadro's constant in the data booklet, you will see that it is just given as 6.02 times 10 to the 23 things per mole. Now, if we just use 3 significant digits of precision, it'll look something like this. This number is known as Avogadro's number. Usually the symbol is capital N with a little subscript A. 6.02 times 10 to the 23. Atoms or molecules, or it's really whatever you're counting. That thing per mole. Donuts per mole. Whatever you're counting, those are the units per mole. Now, usually if you are in the business of counting the number of particles present in some sample, you're also going to be able to more easily measure mass instead of number of particles in a sample. It's much easier to measure mass because you can just put it on a triple beam balance instead of using tweezers to count billions and billions of particles. So how is mass related to moles and number of particles? Well, we have a new unit called the Unified Atomic Mass Unit, and it's abbreviated. The symbol is U, not AMU. That's an older unit. You should not use AMU. It's just U. This was originally defined as 1/12 the mass of 1 atom of carbon 12. If you define 1U as being 1/12 the mass of 1 atom of carbon 12, then what is the mass of 1 atom of carbon 12? It would be 12U. As a mass, 12U. And the strength of defining a mass unit in this way is that now, because carbon 12 has 6 protons and 6 neutrons in it. That means there's 12 total protons and neutrons. And since the mass of one atom is 12U, that means one proton has a mass of roughly 1U, and one neutron has a mass of roughly 1U. It's not exact because there's some things that throw off the mass of one proton to not be exactly 1U. Like there's actually electrons in the atom, and there's this thing called binding energy that we're going to learn about that affects how much mass the constituent particles in an atom have. But it's close to 1U, and if we look it up and find the mass exactly, you'll see that the mass of a proton is about 1.007276U, and the mass of a neutron is about 1.008665U. So they're not exactly the same size, and they're not exactly 1U, but they're close. And for the problems that we're going to do involving moles and counting particles and mass in a gas, we're not really concerned with the fact that 4 significant digits over, there's a decimal that's not a 0. When we learn about nuclear physics, there are some topics where we will need to be concerned with the fact that these are not exactly 1U, but we're not there yet. For now, it's enough that we can approximate their mass as 1U, which makes another thing easy to do. If I tell you that there's an isotope of lead whose mass number is 206, lead 206, you can then tell me the approximate mass almost immediately is 206U, because that's how many neutrons and protons there are, and the mass of one proton is about a U, and the mass of a neutron is about a U, so the mass of that whole atom is about 206U. You can pretty much ignore electrons. They're 2,000 times smaller than a proton, and we're already approximating a proton as 1U, so the electrons aren't going to make any difference in this approximation. Another benefit of defining 1U in this way, how we did with carbon, and the fact that we defined a mole of things to be the number of atoms in 12 grams of carbon-12, is that this mass number, which is a horrible name because it's really not mass, it's just the number of protons plus the number of neutrons. It's just an integer. It's not actually the mass, but it's a close approximation. This, when you have mass number, you can use it as the approximate mass of an atom in U. Measured in U. And also, it's the approximate molar mass in grams per mole. And they did this on purpose so that the number would be the same for both of those, and so that it would be easy to read from the periodic table, or if you knew which isotope you were talking about, you could just immediately see. Lead-206 has an atom of lead-206 has a mass of 206U, and also the number of grams in 1 mole of lead-206 is 206 grams per mole. Let's describe everything we just talked about with some variables. So molar mass is usually capital M. The total mass of a sample is the number of particles in the sample times the mass of each particle. That's the total mass of a sample, where N equals number of particles and little m equals mass of each particle. I'm saying particle because if you're dealing with something like a monatomic gas, which is a gas made of single atoms, then the particles are actually atoms. But if you're dealing with something called a diatomic gas, or a water molecule, or bigger molecules, the individual elementary particles are actually groups of atoms called molecules. So you might be counting molecules, or you might just be counting atoms. It depends on the substance that you're talking about. IB physics doesn't go quite as far into you needing to worry about that. Usually that kind of detail will be given in the problem. Little n is number of moles. Avogadro's number is capital N subscript A. Avogadro's number. So we can relate these variables with a couple of equations. The first one is the number of moles that you have is just the number of particles that you have divided by how many particles there are in 1 mole. So if I was calculating dozens of cookies, if I have 36 cookies, and I want to know how many dozen cookies that is, I would divide by 12 cookies per dozen. That would tell me 3 dozen. Right? This is the exact same calculation we're doing when we do moles and number of particles and Avogadro's number. It's just that we're not using 12, we're using 6.02 times 10 to the 23rd. The other equation that relates all these variables is molar mass can be calculated as total mass, or N times little m, divided by the number of moles, little n. So at the end of the day, you would have total mass divided by the number of moles, which would be mass per mole. That is the concept of molar mass. Now, when I work problems involving all these concepts, I don't necessarily use the equations in every problem, because a lot of the time you can just look at the units and figure out what math to do based on the units. So let's see an example. I'll leave the equations right here. An example would be, how many particles are in 2.5 moles of helium? Helium-4, let's say. Now, I could have said any element, and the answer to this question would have been the exact same, because number of particles in 2.5 moles has nothing to do with the specific element. We're just counting things. The different elements will have different masses because each atom will be bigger or smaller. But number of particles in 2.5 moles is the same no matter what you're counting. And the relevant equation would be number of moles equals number of particles divided by Avogadro's number. We're solving for number of particles, which is capital N, so I can rearrange it. And that tells me I need to multiply moles times Avogadro's number. 2.5 times 6.02 times 10 to the 23 will be 1.505 times 10 to the 24 particles. A further question might be, what is the mass of 2.5 moles of helium-4? What is the mass of all of those particles? Well, you have to kind of build it. We could, now that we know how many particles there are, if we knew the mass of one particle, then we could just multiply the mass of one particle times the number of particles. So that would be capital N times little m. And you could build how much mass there is, or calculate how much mass there is. That's 1.505 times 10 to the 24. Now, you don't really have to go look anything up for the mass of helium-4. It's in the name. Because of the way they defined what 1U is, you could do this calculation in U, and you could get the answer in U. So the answer measured in unified atomic mass units would be 6.02 times 10 to the 24. That number is purely a coincidence. 6.02 times 10 to the 24 U. If you wanted that in grams or kilograms, we could do a conversion. If you look in the data booklet, there is a conversion given for unified atomic mass unit into kilograms. It's 1.661 times 10 to the negative 27 kilograms. So 1.661 times 10 to the negative 27 kilograms is 1 U. And then I would know the mass in kilograms is 0.00999922 kilograms. You don't really need that many decimal places. It's certainly just 0.01 kilograms. And so in grams, though, if you needed it in grams, you could just multiply that by 1,000 and get 10 grams. All right, let's do one more example. Let's say that we have some nitrogen, which will have, let's say, nitrogen 14. And the molar mass of nitrogen 14 is, you guessed it, 14 grams per mole. How many molecules of nitrogen 14? Oh, yeah, hold on. Nitrogen 14 is one of those diatomic gases when it's a gas. So it's actually 28 grams per mole because a molecule of nitrogen has 2 atoms of nitrogen. So let's fix that. How many molecules of nitrogen 14 are in 2 kilograms of a sample of nitrogen 14? Could be a common question. Well, that's 2,000 grams, and there's 28 grams in 1 mole. So when I see this, I just see immediately that I need to divide the mass I have, 2,000 grams, by how many grams are in 1 mole. And if I do that, it's going to tell me that it will take, or that will be 71.43 moles. If you don't just see that based on the units, then you should use an equation. And the relevant equation is the one with molar mass equals total mass over number of moles. So if given total mass and molar mass, you can find moles by rearranging the equation like this. And that tells me I need to divide total mass by molar mass, which is what I did over here. Divide total mass by molar mass. It gives me lowercase n number of moles. I basically know how many molecules there are now, because if you know how many moles there are, it's really easy to get to number of molecules. Number of moles is just number of molecules divided by Avogadro's number. So plug in, I'm solving for number of molecules. That's going to be number of moles times Avogadro's number. So 71.43 times 6.02 times 10 to the 23. And you get 4.3 times 10 to the 25 molecules. Now, if you were given the fact that this is a diatomic atom, a molecule, which means 2 atoms per molecule, someone might ask a follow-up question is, how many atoms of nitrogen is that? If you know that it's this many molecules, you would just multiply that by 2 to figure out how many atoms there are, because each molecule has 2 atoms. 2 times 4.3 times 10 to the 25. And that depends on the specific molecule, and you would be given that information if you needed it. The end.